In this video, we are going to be looking at LC circuits. So let's start with a fully charged capacitor like this, where all of the energy is stored inside of its electric field. We then connect it to the circuit that has an inductor placed in it like so. So now what's going to happen is the positive charges down here are going to start to flow like so through the inductor, which really is just a solenoid, and all the way onto this negatively charged plate. When they flow through the conductor, we know that that is going to generate this magnetic field in that same direction. At some point, there's not going to be many positive charges left to move, so then the magnitude of this magnetic field here is going to be reduced. So B is reduced. When this happens, so when this magnetic field gets reduced a lot, we're essentially in this scenario where there are no more charges left moving, so we have no more magnetic field. Because we went from having a magnetic field to not having a magnetic field, we know that by Faraday's law, a magnetic field is going to be induced to kind of like compensate for that. To get a magnetic field induced in the same direction means having a current induced in this direction, which is like having this EMF that is being induced right here. So the idea is then when our capacitor is fully discharged, we're going to have this induced current that is pulling even more positive charge and placing it onto this upper plate, effectively reducing the polarity between the plates. And we can see this equation here is what we use to figure out what this EMF here, this induced EMF is. So then we go from having all of the energy here to having all of the energy here to then having all of the energy here. So this oscillatory motion back and forth between energy on the capacitor to energy on the inductor and back and forth. Now at any arbitrary point in time t, we can figure out what is the charge on the capacitor and what is the current through the system. What we do know is that delta UE, the change in the electric potential energy, plus the change in the magnetic potential energy has to be equal to 0 because the energy has nowhere else to go. Like there's no resistor, there's no output, it's just going from here to here and back and forth again. So what we say is that, well, we know what this is. This is Q squared over 2C. And we know what this is. It's just 1/2 Li squared. We saw that in the last video. And we want to see, well, how does that change? So we're going to take d over dt of these two values and set that equal to 0. We can go ahead and take the time derivative and we get this. So here we get q over c and then dq over dt plus li di over dt is equal to 0. We're just going to keep it in this format to make some later stuff a little bit easy for us. Now we do have to remember that I is just equal to dq over dt, so let's replace that in this equation here. And so we get q over c dq over dt is equal to negative L dq over dt d2q over dt squared. So that's just from taking that and plugging it in. The reason why we didn't further simplify this on this side is because now we can cancel out the dq over dt on both sides and we get this. So d2q over dt squared is equal to negative 1 over LC times q. Now, if you've taken classical mechanics, you've seen this type of equation before when looking at a simple harmonic oscillator. So by simple harmonic oscillator, we're talking about something like a mass on a spring that's going from this point and back and forth, like it's oscillating with a steady, like sinusoidal pattern. So because we know how to solve that equation for the simple harmonic oscillator, we can essentially just use that solution to say that Q is equal to Q max cosine of omega t plus phi, where omega is just 1 over the square root of L times C, and phi is its phase. If we then look at I, the current, we're going to take the time derivative of Q, so I is equal to dq over dt, take the derivative of this, and we get negative I max sine of omega t plus phi. Okay, so these are our two answers. So this is the charge on the capacitor at any point in time, and this is the current through the system at any point in time. If we were to then look at them together, like we were to plot them, we'd see that whenever we have the maximum amount of Q, that is when our capacitor is fully charged, and that is when we have no current. So that's like at the very beginning scenario where our capacitor was fully charged, place it in the system. Then when we have I max here, we have no charge. And that happens whenever we had all of that charge getting moved. So here we had our plates. All of that charge was running through our inductor, right? So we were losing all the charge here and then gaining all of that in terms of current. So like it was all moving like so. So that's at this point right here. And then you can keep looking at this where we have this oscillatory motion. But what we see is that the sum of these two curves in terms of like where is the energy, is it in the electric field or the magnetic field? The sum of them are always going to be equal to the total amount of energy. So here we have all of the energies in the electric field, none of the energies in the magnetic field, and then vice versa. So all the energies in the magnetic, none of it's in the electric, and so on. There's one more thing that we can talk about, which is just natural frequency. And here, this is a concept very similar to what we've seen with classical mechanics, where we're just going to take our omega value here and do this times 1 over 2 pi. That's our natural frequency because omega is just 2 times pi times f. So this is essentially it. I recommend going to the textbook and reading over it a little bit more because it does give you that analogy between the LC circuit and the spring itself. So saying like at this point here, what does that correspond to when we're talking about a spring mass